A particle crosses a detector, and the screen records two flashes. The first appears at -2, 1. 1 second later, the second appears at 2, 4. Analytical geometry gives each flash an address, but physics asks a more useful question. What changed between them? Before we answer, notice that a point and a position vector can use the same two numbers, while meaning different things. The point P0 names a location. The position vector R0 is an arrow from the chosen origin to that location. Move the origin, and the position vector changes, even though the flash itself has not moved. So coordinates are not the event. They are a description of the event relative to a chosen reference. Two measured locations are our raw geometric data. The story begins when we compare them. Physics is often less interested in either position by itself than in the change from the first to the second. Subtract the initial position from the final position. 2 minus -2 gives 4. 4 minus 1 gives 3. The displacement is therefore 3 meters. This arrow does not begin at the coordinate origin. It begins at the first flash and ends at the second, because it describes the change between those events. Its first component says 4 meters to the right. Its second says 3 meters upward. Components replace a diagonal geometric move with two simple signed changes that are easy to calculate. Together, they still describe one displacement. Its magnitude is the straight line distance between the flashes, the square root of 4 squared plus 3 squared, which is 5 meters. Now shift the coordinate origin. Both position vectors change, but their difference does not. The same 4 right, 3 up arrow still connects the events. That is why displacement is so useful in physics. It captures the relation between two positions while ignoring an arbitrary choice of origin. Geometry gave us 2 points. Vector notation compressed their physical relationship into one object. The detector also recorded time. The flashes are 1 second apart, so average velocity is displacement divided by elapsed time. 3 meters divided by 1 second gives 3 meters per second. The same pair of components now describes a rate of change. 4 meters per second horizontally and 3 vertically. If the motion is uniform between the flashes, we can describe every intermediate position with one equation. Start at the initial position, then add t copies of the velocity. At time 0, the added part vanished, and we are at p0. At time 1, we add the full 3 displacement and arrive at p1. Values between 0 and 1 trace the straight path between the observations. This is analytical geometry simplified by vectors. Instead of deriving a separate relation between x and y, one compact equation carries the starting position, direction, speed, and time. The parameter t moves a marker through the family of points. The arrow is not a decorative pointer, it is the rule that generates the trajectory. And because the calculation is component-based, the same idea scales to many coordinates without changing its logic. Now imagine a second detector mounted at 90 degrees to the first. We want to express the same measured motion in its rotated coordinate system. Recomputing every point one at a time would be tedious. A matrix packages the transformation rule so it can be applied consistently to any coordinate pair. But where do its 4 numbers come from? Ask what the rotation does to the 2 basic coordinate directions. The first basic direction points 1 step along x. After a 90-degree counterclockwise rotation, it points 1 step along positive y. That output, 0, 1, becomes the first column of the matrix. The second basic direction points 1 step along y. After the same rotation, it points 1 step along negative x. That output, -1, 0, becomes the second column. Place those two transformed directions side by side, and the rotation matrix appears. 0, -1, 1, 0. This is the geometric meaning hidden inside a matrix. Its columns record where the basic coordinate directions go. Once those two outcomes are known, every other direction follows from them. The matrix is not a box of unexplained numbers, it is a compact machine built from the transformation of the coordinate grid itself. Our displacement, 3, means 4 copies of the first basic direction plus 3 copies of the second. A matrix transforms that vector by transforming those ingredients and recombining them with the same weights. 4 times the first matrix column plus 3 times the second gives 4 times 0, 1 plus 3 times -1, 0. The result is -3, 4. Matrix vector multiplication is therefore a weighted combination of the matrix columns. Geometrically, the original 4 right 3 up displacement becomes 3 left 4 up after a 90-degree counterclockwise rotation. Its length is still 5. The coordinates changed because the direction changed, while the physical size was preserved. Now apply the same matrix to both detector positions. The two flashes and the line between them rotate as one coherent event. Straight lines remain straight, intersections remain consistent, and every coordinate obeys the same rule. This is why matrix operations simplify analytical geometry. One transformation acts on an entire structured picture, not on isolated numbers. The determinant of this rotation matrix is 1. From the previous video, a non-zero determinant means full rank, so no independent direction has been collapsed. The transformation can be undone, and no geometric information is lost. In the next video, we will compose transformations by multiplying matrices and reverse them with inverse matrices. The same architecture reaches quantum mechanics. A quantum state is not generally an arrow in ordinary detector space, so we will not pretend that it is. But the algebraic pattern survives. An operator U acts on a state psi to produce a new state psi prime. Today we built the visual intuition underneath that pattern. Geometry supplied points. Vectors described relationships and motion. Matrices transformed the whole coordinate story with one consistent role.